So welcome to the fifth session of the 2025 Autumn Series on Light. Most of you know I'm Alistair Nunn, I'm Director of Science of the Gaia Foundation. And today we are delighted to welcome Dr. Roger Seheult. Is that correct, Roger? As our main speaker. I'm going to do a little bit of a background about setting the scene and just do a bit of a recap to where we've been with this series. Basically, what we're talking about today is light in the modern environment. And from my perspective, certainly as a biologist, it's all about evolution and where we've been and where we're going. Certainly, Darwin would have recognized the problems we may be starting to endure with the more modern environment. And I should apologize for this slide. I've shown this before, but I think this is a fascinating one. And this is the idea that, of course, a lot of what we see today in our vision and light, it's all down to water. Water itself has a very defined transmission spectrum. And this is a picture I've shown before, but it shows quite clearly that blue and green light is very transmissible through water. And this is just how far it may go into seawater. But at either end of the spectrum, in infrared and in UV, it's much less transmissible. And the key differences here, and we talked about this before, was the fact that UV, far UV, actually can start to cause free radicals and photolysis water, whereas infrared tends to warm water up. But this basically means all of our biology and everything is related to this kind of spectrum of light. And one of the things we kind of got to go back to, and this is where we start from, is evolution and the origins of life. And life has evolved on this planet. It's indeed an emergent property of the planet. And it's become canalized to the environment we find. And in previous lectures, we talked about gravity and atmosphere and everything. But light, of course, is another one of these things. Now, what's quite interesting is that actually humans in particular, we can survive without light, but not very long. And we certainly don't thrive. And one of the things we're beginning to realize that these little chaps, the mitochondria here, tend to also do better with the right kind of light spectrum. And this is just the emerging evidence coming out now, but it seems to make sense from evolution. And indeed, talking about mitochondria, it's often worth thinking about where these guys come from. Now, one of the best origins of theory, and I'll put a rider here, there are origins of theory, other origins of life theories, is that life actually started or could have started in an alkaline thermal vent. And this is reliant on basic physics of self-organizing dissipating systems. And the reason for this, we think it's important, is because this is a proton gradient. And this is old Peter Mitchell, who many of you are biochemists will remember to develop the theory of chemiosmosis. So very early in life's origins, it seems that these autocatalytic networks started to come into formation. This is sort of led to the Krebs cycle, but also electron transport. And this is quite critical. But not long after life got going, and we don't know exactly when, and there's a possibility that the first life form was what we call the last universal common ancestor, Luca. But we're not entirely clear on that. But certainly not long after that, there seem to be at least two kingdoms evolved. One of them was bacteria, and the other of these things called archaea, which are emerging to be a really fascinating group of they're prokaryotes, they're single cells. And sometime in this period, and we're not entirely sure when, photosynthesis started. Now, this may have started using rhodopsin, and so it didn't use oxygen, or it may have been chlorophyll. We're not entirely sure which one started first and for how long, but certainly one of these got going. And this led to obviously oxygen, and I won't go into the quantum mechanics of this, but the key thing I want you to note here is that at some point, billion to 2 billion years ago, may even be older, an Archaean cell and a bacterium got together, and there was a big love story, and this led to the modern eukaryotic cell. And the key message here, of course, this puts mitochondria, who are the sort of the downstream progeny of the bacteria, is they're involved in everything in the cell. It's not just they produce energy, they're involved in controlling stress responses, how it grows, how the cell dies, control of calcium, sodium, potassium. They're involved in just about everything, including metabolism. So they're central to everything. And for art lectures anyway, in this series, one of the key things here, and I'm sorry, I apologize for this slide, I've showed it before, but of course, was people were starting to understand, well, back in the 18th, 19th century, well, how does life work? And respiration was one of the key ones. Why are cells using oxygen? And they discovered that there were these things called cytochromes in a cell. Well, what's a cytochrome? Well, it's simply a colored molecule in a cell. That's a description of it. But critically, three were discovered, and these had particular absorbance frequencies, peak absorbance frequencies, ranging from the green up into towards the red. And one of the key things about these was, of course, if you change the oxidation status, their absorbance changed. And this suggested if light was shone on them, this indeed would also change the redox or electron flow. And in fact, we know this to be true because if you remember this slide, this is the muddy mitochondrion. What color is a mitochondria? Well, we think it might be kind of muddy brown color. Why is this? Well, because it absorbs light of multiple frequencies. And if we think about complex 1, the first complex, this doesn't have a cytochrome, but it does absorb in the blue as well as other frequencies, and it has things like flavins and nicotinamide in it. But complex 3, and this is one we talked about a few weeks ago in some detail, absorbs green, but it also absorbs other wavelengths too. And this is a key point, is that although there's a peak absorbance, it absorbs anything from blue all the way up to red. And the one, of course, we're all interested in, Glenn's particularly interested in, is cytochrome C oxidase. And of course, this absorbs, again, right through the wavelengths, but particularly up into red and infrared. Now, some of this could be directly due to the molecule, but it could also be due, and we don't know yet, due to ordered water. So we won't go into that today. But the key thing here is if you alter the state of the electron transport, you alter absorbance, and equally, if you absorb a photon, you alter the redox state. So there's a direct interaction, or a theoretical, and we know a real interaction between light and electron transport. And why is this important? Well, you remember we talked about the Goldilocks zone. Now, something we've always very much been involved with and got to believe is really, really important in biology is this concept of hormesis. This is effectively what doesn't kill you, make you stronger. But of course, this goes right back to evolution and adaptation through natural selection. Small amounts of stress induce biology to adapt to that stress. Too much doesn't do it any good. And certainly life would never evolve without stress. If we didn't have a changing environment, life wouldn't have got going. And it seems to operate, this natural selective process of these organized structures, seems to happen at all scales. And here I've just got a graph showing blue, green, and red light. Now we know, and this is from Michael Hamblin's group, that the power density and the time we expose cells to of light frequencies has an effect between stimulating and inhibiting. And this is kind of reflected in the energy status. Blue light has more energy than, say, red light. So dose is key. And this also begins to explain when we look at the literature today on, say, photobiomodulation, there's an awful lot of variability in the data, and some people say it does this, some people says it does that. But of course, this is down to hormesis and cell state. And this is a paper I've shown before, but this is one of the best papers I've found. And this is where this group of Glavinska, they've shone light of different light wavelengths onto mitochondria, and they've inhibited each of the complexes and shown quite clearly there's a preferential effect, say blue, green, and red light on each of the complexes. But in particular, when you get to the higher energies, you start to see a clear biphasic response, certainly up at the blue end. There's less on the red end, but I suspect that's because they simply haven't had high enough intensity. And indeed, there's certainly evidence of very high levels of infrared, and red light will actually damage biology. But most of the time, we're not exposed to that, possibly in front of a smelting furnace or something, or indeed sitting by the sun. Now, there's another factor here, and this is kind of leading into the health thing, of course, is that biology is very interesting, and it's reliant on stress to evolve. But if you take away the stress, it doesn't evolve, it actually goes backwards. And we published this little paper years ago, and we were actually trying to explain Fermi's paradox, which is why we're aliens here. But the key point about this is that biology seems to have evolved to try and modulate its environment, because any biology or any organism doesn't want to be constantly stressed, so it tries to change its environment. And the key thing is humans have got really good at doing this. And we've bummed along for billions of years down here being totally dependent on our environment, but suddenly with technology, we switched. We can change our environment to make our lives very, very comfortable. And we're kind of seeking utopia, which of course doesn't exist. But what this actually means, and we suggested this, there is some evidence this in the literature, that of course we're removing the very things that made us smart and adaptable in the first place. This is a kind of intelligence paradox. And of course, through evolution, we've been dependent on temperature. We've been controlled by temperature, starvation, physical activity, in particular, predators, bitter food, polyphenols are important, and particularly light intensity and its spectral shifts during the day and circadian rhythms. We've got a whole new environment now, which takes away a lot of this. And the link here, and this is one of the things we suggested many years ago, was that actually this modern lifestyle, and by that I mean the modern sedentary lifestyle, where we've got all our labour-saving devices, we drive everywhere, we sit in our buildings, don't have to lift a finger to do anything, well, certain populations anyway, not every population, then overfeed ourselves. And the emerging evidence is actually, for instance, physical activity is very important for stimulating mitochondrial reserve. And in fact, we rely on it to develop this, what we call metabolic flexibility. And one of the explanations, for instance, of something called the metabolic syndrome, which is a phenotype where you're seeing with increased visceral adipose tissue, insulin resistance, high blood pressure, altered lipid profiles, is potentially driven by inflammation. And one explanation for this is, of course, if you live a very, very sedentary lifestyle and then expose yourself to all sorts of horrible foods, you actually stress the system and it can't adapt, and you end up with these very, very poorly mitochondria. And we've described this, and we've mentioned this before, this idea of the metabolic flight envelope is that without the stress, you've got a very narrow envelope to stress. And if you're stressed by something, you can't very adapt. But if you're very healthy and fit, you stand a much better chance of doing well, and in particularly not developing chronic inflammation. And it seems that we're not alone in thinking this. And this is just an example. And I put this slide in. This is for Roger, really. Soon as the pandemic started, the COVID pandemic, because we were thinking like this, we thought, well, which populations of people might be more susceptible to the virus, the COVID virus? And one of the suggestions were populations who probably had less than optimal mitochondrial function. And this certainly seems to be the case because, as after a lot of research, certainly in reading, viruses modulate mitochondrial function for their own nefarious ends. And if you haven't got the mitochondria reserve, they just get stressed and you can trigger inflammation. And this seems to be the case, and there's emerging evidence now that exercise has been a powerful way of overcoming this, or at least preventing it in the first place. It doesn't get rid of it completely, but it does seem to be a real effect. And now I'll just throw this in, and this is one to think about slightly out the box. And I put this in right at the last moment. Thinking about the built environment, we're all talking about buildings and everything. But I'm a pilot. I fly one of these things a lot. It's a glider. I've been doing it for 40 years. But I also drive one of these things, a car. Now, when we actually start to look at the glass in these things, the glass in particular in cars is quite interesting. It blocks the UV, but depending on the type of tinting and where it is in the car and type of glass, it allows the infrared in. So back to very old type style glass. But the other thing is a lot of vehicles and a lot of aircraft rely on acrylic, the plexiglass, the perspex kind of. And this has a very interesting transmission profile. It blocks most of the UV, but allows a lot of the infrared in, suggesting, do we go to acrylic windows? And it's actually very clear, and this is me sitting in a glider, and it's very, very clear. So most of the time I'm sitting in one of these things, I'm being exposed to very little UV, but a lot of infrared. What that means, I don't know yet, but maybe, Glenn, there's a very nice experiment here for us pilots. Anyway, I shall now move on to Roger, the main course, as it were. Roger's an associate clinical professor at the University of California and at Loma University. In 2012, with a work colleague, he founded MedCram, that's an interesting title, a medical education company, and is producing CME accredited videos, which is used by multiple medical outlets, hospitals, medical professionals from all over the world, with well over 1 million YouTube subscribers. He's a quadruple board certified physician, and he's published on anti-inflammatory approaches to COVID-19. I know you published other things, Roger, but I'll pick that one out. And he's won multiple awards, including the William Cobra MD Award for Outstanding Contribution to Medicine. The key thing is he has a real passion promoting health lifestyle and demystifying medical concepts as a medical communicator. And I note he's got these 8 pillars of health: nutrition, exercise, water, sunlight, temperature, air, rest, and trust. An interesting one. And of course, using light as a medicine. Anyway, I would now like to pass over to Roger, and I'll stop sharing. So off you go.
Thank you so much, Alistair. That was a wonderful introduction. I actually am from Loma, which is the west coast of the United States. But I happen to be here in Ohio, which is on the Eastern time zone. So it's 10 o'clock in the morning here. I know it's 3 in the just after 3 there in England. But I'm here actually at the Charles F. Kettering House for a presentation later today, and they've been gracious enough to let me use their office here. It's a wonderful house. It's the house of a industrious tycoon living back in the 18 and 1900s. And it's really one of the legacies of America's great problem solvers. And it really sums up what we're about to talk about today. Kettering, who built this house, helped invent the electric self-starter of the engine. He wired cars and farms for electricity. He helped make modern air conditioning possible. And in many ways, this house is one of the very first prototypes of the fully engineered indoor environments. But it's also, his story is a cautionary tale. To solve, for instance, engine knock, he helped introduce leaded gasoline. To make cooling safe and convenient, he helped bring Freon into refrigerators and air conditioners. Both were brilliant engineering solutions, and both, as well, we later discovered, carried enormous unintended health consequences and environmental costs. What's fascinating is that Kettering also invested in understanding how light affects biology. He actually helped fund research on chlorophyll and photosynthesis, literally how light powers living systems. And with Alfred Sloan, he co-founded what became the Sloan Kettering Institute for Cancer Research, applying industrial scale science to one of the great diseases of modern life. Alistair, I just noticed that you fly gliders. They told me here when I was checking in and setting up that Amelia Earhart would fly in on an airstrip not too far away from here, and actually got some health things related to her health issues here at the Kettering Institute. Even in his own career, though, Kettering on both sides saw technological progress that quietly reshaped our environment and serious attention to how that environment, including light, affects health and cancer biology. And that's the frame that I want to use tonight as we think about light and health. In the last 100 years, we've done something just as radical with our light environment. We've moved from living under a changing spectrum of sunlight and darkness to living indoors behind glass under LEDs and screens that were designed for visual efficiency and energy savings, not for biological compatibility. We fixed darkness with 24/7 light. We filtered and reshaped the spectrum that reaches our eyes, our skin, and our mitochondria. And only now are we starting to see the bill, which is disrupted sleep, circadian misalignment, metabolic problems, mood disorders, patterns that line up uncomfortably well with this new artificial light world. Kettering famously said, "A problem well stated is a problem half solved." So my goal in this talk today is to state the problem clearly. Our modern light environment is a magnificent technical achievement, but also a biological mismatch. Kettering also said that my interest is in the future because I'm going to spend the rest of my life there. In that same spirit, we're not here to be nostalgic or anti-technology, quite the opposite. We're here to ask, knowing what we now know about light and human biology, how can we redesign our homes, hospitals, and cities so that innovation and health move in the same direction? And that's the journey that we're going to start to take this evening. This here is a picture of actually one of my alma mater, Loma University, and a university that actually started off with those ideals and understanding of our environments and light and health. This is the Kettering house where I'm broadcasting from tonight. This is Charles Kettering, as you can see here, an industrialist. And let's move in real quickly. So we've talked about light and the electromagnetic spectrum. I think that's really important to understand in terms of where we're going to go. It's a continuous spectrum, and we've kind of arbitrarily broken it up into that light that we can see with our eyes, which is kind of arbitrary, and all that stuff that is to one side and the other. Ultraviolet light, we know about vitamin D and nitric oxide. We're not going to touch on that today. Visible light has impulses in terms of circadian rhythm, mood, and nociceptors, as we talked about earlier in this series with green light. But today we're going to focus on infrared light on the other side of the spectrum. It's mitochondrial effects, cytochrome C, and structured water and things of that nature. As you can see here from the spectrum, that more than 50% of the photons from the sun come to us in that infrared spectrum. Low energy, non-ionizing, but can penetrate very deeply. This is a problem because this study, which was performed in 1992, okay, so this is a very long time ago, even at that time, we were only spending, as Americans, about 7.6% of our lives outside. I think in Great Britain, they do a little bit better job than we do here in the United States. But even since the pandemic, you can see here that the amount of time spent out of home has been declining and dropped precipitously during the pandemic, and we have not recovered. So this is becoming a bigger and bigger issue. Our environment in our homes is really what's defining our life. And so I tell you this, I say that the enemy of longevity is chronic disease. If you want to live a long and healthy life, you want to avoid diseases like heart disease, diabetes, obesity, dementia, inflammation, long COVID, and cancer. And if you look at the research on this from a medical standpoint, really at the heart of much of this, at the epicenter of much of this, is mitochondrial dysfunction. You can actually look this up on many studies, and you can see the mitochondria, if you like to think of it, is like the engine in our car. It uses fuel, produces energy in the form of ATP, gives off carbon dioxide. And just like a car and its engine, which produces locomotion, it also generates heat. And if that heat is not dealt with efficiently, it will reduce the efficiency of the engine and maybe even shut it down. And so an engine in a car has a cooling system, has a radiator, has a water pump, and it has a system in place to deal with that natural side effect. Well, the mitochondria also has a natural side effect of its workings, and that is oxidative stress. For those of you who are nerded out on biochemistry, you'll know that at the very end of the electron transport chain, 4 electrons need to be transferred to oxygen, and it needs to be done efficiently. And if all 4 electrons are successfully transferred, which usually happens, you get a water molecule. If you don't, you get either a superoxide in 1 electron, a hydrogen peroxide with 2, or a hydroxy radical with 3. And this can immediately damage any surrounding structures within angstroms of its production. And so oxidative stress, just like heat, needs to be dealt with. And there actually is emerging evidence. Russell Ryder and Scott Zimmerman published the paper that really got me interested in this in 2019, titled Optics or Melatonin, the Optics of the Human Body, which clearly demonstrates and proposes that melatonin, probably one of the most powerful antioxidants known to man, is produced on site in the mitochondria and is one of the things that actually deals with oxidative stress. As it turns out, there is a system in place that doesn't require a supply chain, that's very easily accessible and is available. You just need to go outside to get it, and actually can upregulate production of melatonin, and has been proposed and is looked at as doing this. And it is, in fact, sunlight. And we're going to talk a little bit about the evidence behind this and other things that infrared light does. Now, this is a quote from that paper, 2019. It has now been shown that the mitochondria produce melatonin in many cells in quantities which are orders of magnitude higher than that produced in the pineal gland. This subcellular melatonin does not necessarily fluctuate with our circadian clock or release into the circulation system, but instead has been proposed to be consumed locally in response to free radical density within each cell, in particular in response to near infrared light exposure. You can see greater than 95% of the body's melatonin is subcellular in the mitochondria. Interesting aspects of infrared light, as we'll talk about. This is a study that was published at the University of Warwick in Coventry, showing very clearly that infrared light has the ability to penetrate through materials, in this case, clothes. You're needing here just maybe even just 1 or 2 layers of clothing, and on average, about 60 to 80% of infrared energy can penetrate through that type of material. We've known for a long time that the longer the wavelength, the more ability there is to penetrate through objects, including our body. This is a figure from that 2019 Zimmerman and Ryder paper, showing at that time that they proposed up to 8 centimeters that infrared light could penetrate through the human body. And because of that, they believe that much of the body's mitochondria is actually in the window of transmission of infrared light to the human body. Of course, we've got a newer paper, this one published by Glenn Jeffrey just this year, titled Longer Wavelengths in Sunlight Pass Through the Human Body, which have a systemic impact which improves vision. And really, I think a lot of the aspects that we're going to talk about today with infrared light is really combined in this study, which I think is a great study to introduce people to the understanding of infrared light. In that study, of course, it showed, this is actually Bob Fosbury's hand, showing clearly the transmission of infrared light through the hand, through bones, without any problem. And then, of course, the more mind-blowing photograph is the one on the right, showing the passage of that light through 30 centimeters of a thorax and essentially through the entire human body. They also demonstrated, once again, the ability of infrared light to penetrate through clothes, in this case, nearly 100 times more transparent at 850 nanometers than visible light. And this was published in that paper as well. Again, what they showed here is this is the transmission, this is the light that was obtained at the entry point of the human body. And then, of course, on a much smaller scale, the transmission coming through the other side, demonstrating not only that infrared light can penetrate through the human body, but also much of it is absorbed and doing something inside the body. And you can clearly see that here with this experiment. The interesting aspect about this, of course, Glenn Jeffrey being in the Department of Ophthalmology, they're interested in the eye, and the retina having to have the highest concentration of mitochondria in that tissue, specifically the green cones, we'll call them, the red cones and the blue cones, which detect that type of light. and are extremely dependent on having energy. Think about this as updating so many times per second and sending neurotransmission to the brain so that you can not only tell in exquisite detail what you're seeing, but it can be updated literally in milliseconds. And of course, the cones of the eye have the most amount of mitochondria. And so really, this is going to be where we're going to see a difference. Red cones having a protan, green deutan, and blue tritan perceived color issues. But what they showed essentially was when they transmitted 850 nanometer light to a control group, actually by not turning the light on, to a group with both the head and the body receiving that light, and of course just the body in the third group, what we saw there is not only evidence that infrared light coming into the body had an effect on mitochondria in terms of upregulation, but also the abscopal effect, which is this idea that shining this light through the body and affecting mitochondria in different organs can actually upregulate those mitochondria distal to that. Now, of course, there's actually a number of papers that have been published on this idea. There's even a paper that I was able to find showing free floating mitochondria in the blood. Yes, you heard correctly. Free floating mitochondria in the blood outside of their cells. So there's obviously a lot that we don't know here. But what we do know is that infrared light can penetrate through the human body and has systemic effects that are quite remarkable. And if you think about that, that should completely change your idea about the potential possibilities of what getting outside into the sun can do. Another aspect of infrared light is the fact that it is highly reflected by any type of green leaves or grass, not because of chlorophyll, but because of the actual structure of that leaf. This is an infrared. Let me tell you a little bit about this. This is a film that you can put over your smartphone camera that does something called an anti-Stoke effect, which is basically when the electron is excited to a particular energy level, and when it drops back down, it drops back down at a higher distance, therefore giving off a photon of light that is higher in energy and has a shorter wavelength. So essentially what this does is it takes infrared light and bumps it up into the visible red spectrum. And I want to show you here what this looks like on a nice day. So this is even on a cloudy day, how much light you can get from just being outside, even though the clouds are blocking the sun. I'll show you now what a sunnier day looks like. So that's quite remarkable. And so let's just summarize what we've talked about here. Near infrared light penetrates deeply through the skin, affects the mitochondria, reduces oxidative stress through that proposed mechanism of melatonin, increases ATP, increases carbon dioxide through metabolism, and actually can decrease the fuels that are necessary for that, reducing glucose. This is a paper that was published by Glenn Jeffrey back in 2024 showing the same thing with 670 nanometer red light on the back in a randomized blinded fashion. It showed that after a glucose tolerance test with 30 subjects, there was a 27% reduction in glucose. So clearly systemic effects. And you can see here that there was a statistically significant reduction in glucose. And at the same time, there was a statistically significant increase in exhaled carbon dioxide. Again, it's very suggestive that this is an increase in metabolism. So if we see the pathophysiological effects in individuals and studies, we should also see evidence of this epidemiologically. This is a University of Oxford and University of Leiden study where they did a blood draw on 10,000 subjects and looked at the weather report in the previous 7 days. It was not temperature, but rather sunlight, and specifically hours of sunlight, that was linked to increased insulin sensitivity and a reduction in triglycerides, showing that, again, systemic effects, and also something working as quickly as just 7 days in terms of turning things on. This, of course, is a major paper that was published back in 2016, 30,000 Swedish women. This is known as the Southern Sweden Study, published by the Karolinska University Hospital. It showed that when they looked at women over 20 years, The women who had the most active sun exposure had a reduction in mortality, not in all cause, but also in cardiovascular and cancer. So all of those categories. Women who avoided the sun at this very northern latitude had an increase in all cause mortality from cardiovascular disease, cancer, and others. In fact, the difference between these two groups was so large that women who had the most active sun exposure and smoked had the same mortality rates as those women who avoided sun and did not smoke. And that's quite impressive. I always joke with my colleagues, we when we tell them to go on the smoking break, they're outside for 15 minutes and we should follow them and get the same benefit, although we should not follow them too closely. Maybe wait another 15 minutes or so. Anyway, but Richard Weller, who was recently on this podcast, on this lecture series, published a paper that was not too dissimilar from this one, 10 times the number of subjects, both men and women, 12.5-year follow-up, and showing essentially exactly the same results for solarium use and for outside use as well. Again, all-cause cardiovascular cancer and non-cancer, non-cardiovascular, a reduction in mortality in all of these except for one, which barely did not make statistical significance. And then when looking at melanoma, and the increase, again, there was a trend to a increase in melanoma, but not statistically significant, and of course, no statistical significance whatsoever in mortality. Now, I talked about the effect of infrared light from trees and green spaces. This is a meta-analysis of 143 studies done and published in 2018. Looking at people living in green spaces, there was a 28% reduction in diabetes, a 16% reduction in cardiovascular mortality, and a 31% reduction in mortality. Now, this was an association study, and many people criticize this by saying, well, sure, people who live in green spaces have higher socioeconomic status. They have more access to healthcare. Of course, they're going to be healthier, people who have the money to live in green spaces. Well, there was an interesting study that was done called the Green Heart Louisville Project. This was just published about last year. Interesting study. They looked at a 4 square mile area in South Louisville, Kentucky. They measured everyone's HSCRP levels, which is basically a surrogate measure of inflammation. And they then got a shovel and literally dug 8,000 holes in the ground and planted 8,000 mature trees from 2019 to 2022, went back and remeasured everybody's and the same people, 745 people's HSCRP. And without without any kind of government assistance, without any kind of guaranteed income, without any exercise program, just leaving them up to their own devices 2-3 years later, just by planting those 8,000 trees, there was a 13 to 20% on average drop in everyone's HSCRP. And that correlated to about a 10 to 15% drop in cardiovascular disease and strokes. Really kind of putting a stake in the heart of the idea that what we're seeing with green spaces is a association with socioeconomic status, but rather something real is happening in that case. And that's important because once again, we're only spending about 7.6% of our lives outside as of 1992. I'm sure that's gotten worse. So really, we ought to focus then. If we're getting so much of this benefit from being outside, what about our living environment? And you can see here what we've done in terms of, let's talk about lighting first of all. We have the solar spectrum, which is this in orange, which obviously goes well into the infrared spectrum. And then we have the incandescent bulb, which mirrors this to some degree, although it has less of that blue light in it. But it does go into the infrared spectrum. Now look at the 3000K LED, which is designed specifically to only give off light in that visible spectrum. And so we're missing a lot of that infrared light in that situation. Now that's important because since 2015 to 2020, about 47% of homes now use LED, whereas before it was only 4%. So this is a definite change in just 5 years. Some of this is through legislation. There was in the United States a rule in 2023 saying that the bulbs that are sold as general service lamps had to be up to 45 lumens per watt or above 45 lumens per watt. Now, an incandescent bulb gives off at about 15 lumens per watt. And as a result of that, these incandescent bulbs were essentially outlawed. You can still get them if they are for specialties or for microwaves or things of that nature. But as a general service lamp, as we define it in the United States, they're no longer available. We now have to use things that are 45 lumens per watt. That rule is going to change. I don't know if that's going to make it to Great Britain or not. I certainly hope it doesn't. But in 2028, the rule is going to change to 125 lumens per watt. And the reason why that's important to understand is that a lumen is a measurement of particularly yellow-green light. And so the only way that engineers can really get to this type of situation, this is a standard that was created in 1924, is by squeezing out some of these other healthy functions that you might see in light that our eyes just aren't seeing. So we're essentially being kind of arbitrarily discriminatory against some of these other wavelengths just to get a lighting that meets a standard. Now, why is that standard there? It's because of efficiency and because of energy efficiency. The other issue that we see in our environments is a window. So we have windows that simply block infrared light from coming in because, again, infrared light is heating in effect. It's typically the type of light that you feel from the sun, or infrared light is the type that you feel that warms you. It's because it's penetrating deeply and warming up your body. It also warms up your house. And so people who want to not spend a lot of money on air conditioning are going to reduce that type of light. And so you can actually get glass that blocks that. In fact, in California, where I live, you cannot get a permit to build a house unless those glass are specifically set at a energy efficiency to reduce the amount of energy. So this is really becoming very widespread. Now, this is that same film that I used on my camera before, and I'm taking this picture from inside of my house where I had all of my windows replaced before I knew all of this, of course. And I don't know if I'd have much of a choice, but you can see I'm taking this picture at daytime, and outside of my home is a bunch of nice trees that are reflecting all of this infrared light. And really, this picture is worth 1,000 words because, first of all, you can see that my home environment is devoid of that wonderful infrared light, number one. Number two, you can see that the part that is coming through the transparent glass is sufficiently muted so that this is the amount of infrared light I'm getting through the window, whereas when I open this window, you can clearly see the amount of infrared light that should be coming into our environment, but it is not. Russell Ryder and Scott Zimmerman published this paper, wonderful graph, basically estimating, because of these two issues of lighting, and windows, what has happened to the amount of infrared light that has come into our bodies over the last 200 years. And I think that's really important. And Glenn Jeffrey's paper is really a look into exactly that issue. This has not yet been published, but is being refereed and is probably going to be coming out very shortly. This is where Glenn took 22 subjects in the LED environment 8 hours a day for 2 years and split them into 11 subjects each, where one got the LED environment, the intervention group got the LED environment plus a 60-watt incandescent lamp on their desk for 2 weeks at work. And the others did not get that 60-watt incandescent. Remember, the incandescent has infrared light. And then they used the same sensitivity contrast testing that we saw previously at 2, 4, and 6 weeks. This is from the research. You can see here that nice glass that's reflecting that infrared light out. Makes it look like very similar to my living room that I just showed you, very dark, except for the light coming in through the window. And you can see here in the upper corner here at A, this is what that work environment looked like. It's kind of awkward, I have to say. I'm presenting this and Glenn Jeffrey's listening to me here, so I hope I present this correctly, Glenn. This is what it looks like. This is what it looks like with a infrared camera. And this is honestly, B is really what a lot of our environments look like with an infrared camera. Here is C again. Now, if you can look over here, you'll see that there are a couple of lamps that were off. Look back here at A. See how that lamp is off, but now it's on over here. See how that lamp was off over there and it's on now. Now we do the same photograph with infrared light and we can see we're getting some infrared light. Now, let's take a look here at the control group. The control group had 100% on the contrast group, and you can see no difference after 2 weeks of doing this. There's really no difference. Why? Because they're not getting any infrared light. But you can see here clearly that that group that got incandescent added. So here's the key point is you didn't have to necessarily replace the LED environment. You just had to add to it this type of infrared from the incandescent. You can see clearly there was a dramatic across the board in both the protan and tritan groups, a reduction in this threshold, meaning an improvement in the ability to discriminate color, probably implying an improvement in mitochondrial function. Now, this is from a different group. This is Gimenez et al. And they did a very similar experiment. Instead of using an incandescent bulb, they used a 850 nanometer wavelength NR light, which is exactly the same wavelength that Glenn used in his first paper that we talked about. And notice here, this is really interesting. They did notice an improvement at the 6.5 joules per square centimeter, but notice that it was only observed, this improvement was only observed when they did the experiment in the wintertime. Now, that's really telling to me, because what it tells me is that during the summertime, they're probably getting enough infrared lights outside of their work environment, perhaps when they leave and the sun is still up, or when they're coming in the morning and the sun has already risen up. And as a result of that, added extra infrared light is not making much of an improvement. I think that's really telling, and it tells me that what we're dealing with here is a deficiency in infrared light. So I'm not the only one that has looked at this, and neither here listening. Again, this is Richard Weller, looked at this, and I want to note here that he's a dermatologist, and this is published in the Journal of Investigative Dermatology, probably one of the Oregon journals of dermatology study. And they said, look, they're realizing that sunlight has actual benefits. There was a Australian panel, of all places, where we have a lot of skin cancer in Australia. The Cancer Council of Australia and Australian College of Dermatologists have both just put out position papers recognizing that sunlight has beneficial effects, and that should be considered in formulating policy on sunlight exposure and highlighting the necessity of carrying out further research. He ends his review here with, "We should take note of that." I believe we should take note, and I took note. It's kind of my own journey to how I got to where I am here as a critical care physician during the pandemic, and sort of piggybacking on what Alistair just mentioned in the introduction. You know, COVID was a massive hit on us in terms of oxidative stress. Just to sort of review, when I started looking at this, again, our mitochondria, which is sort of the epicenter of a lot of these diseases, the receptor for the SARS-CoV-2 virus is ACE2, and ACE2 does more than just receive a virus. It's also a modulator of oxidative stress. And as you can see here, when the SARS-CoV-2 virus binds ACE2 and knocks it out, you're essentially knocking out your water pump. You're knocking out your radiator. In a car where maybe you're running a little hot because you've got some metabolic disease and you're not able to make it up the hill. This is actual data looking at oxidative damage in the mitochondria using F2 isoprostanes as a surrogate. You can see across the board that as you get older, yes, you get oxidative damage, but at every single one of those points, people who were COVID positive had much higher levels of oxidative damage, indicating that once again, oxidative stress is the enemy, as we're talking about. So here's the analogy. We have different cars. We're all driving on the freeway. Some of us have engines that are running nice and cool because we're fit and we're not overweight. Some of us have other issues, chronic conditions. And while we're still running on the road, our thermometer on our engine is running a little bit hot. And we're all coming to this hill called COVID-19. And for some of us who made it up that hill, we got through that. For others, you know, their engine pooped out because it overheated. And if we look at the actual people who did that, what kind of diseases they had, it's the same list of diseases that we mentioned at the beginning that were mitochondrial in nature. So that really made me stop and think about this. The other data from University of Heidelberg and many other studies that showed that people who had normal vitamin D levels and were hospitalized with COVID did fairly well. They actually had a good survival. It was those people with low vitamin D levels that did not do well. Of course, this was an association study, and association does not mean causation. But of course, as a physician, you think that it might be beneficial to give vitamin D, and we did not notice much benefit with giving vitamin D in these types of patients. So it hit me that maybe vitamin D was not doing the heavy lifting, but it was a marker of something that was. And in this case, I believe it was sunlight. So I started looking at data around the world to see if that would that would show. This is Stephen Walren's work that was published in 2021, shortly after the surge in COVID in Europe in the autumn of 2020. He looked and found that temperature really did not predict which country was going to surge in the autumn of 2020. Humidity did not predict at all. Those are R squareds of 0. But what did predict it very well, up to an R squared of 0.77, was the latitude. Started in Finland. We of course know that in the mid section of 2020 in July, Italy was hit really hard. But as the sun started to peel away from the northern hemisphere, we noticed that there was a definite progression and fall of these countries one after the other. In fact, if you were to line them up in a way that looked at the observed day of the second COVID-19 wave surge as a function of the day when the country's sun ultraviolet B daily dose dropped lower than 34% of that at the equator, there is a R squared of literally 0.9993. And Stephen Wallren published this, and you can see clearly that it's almost like clockwork. Like this is almost like you're just sitting in the lab doing V equals IR on resistors. It's quite impressive, the actual R squared on that. More data, this was published at University of Edinburgh. We looked at UVA and mortality from COVID-19 in areas where there's no vitamin D production at all. And as you can see, USA fit the mold, England fit the mold, Italy fit the mold. Basically, the author said it suggests that optimizing sun exposure may be a possible public health intervention. Given that the effect appears independent of a vitamin D pathway, it suggests possible new COVID-19 therapies. So I actually teamed up with Margaret Scutch, who's out of the University in Mexico, and we looked at the entire world's population and latitude and mortality. And we found that for those countries that had more than 50% of the population being overweight, there was a definite association with COVID-19 and mortality and latitude. And we published that back in 2022. But here's the real piece de la resistance. Here's the real coup de grace, if you will. And that's this. If you look at all of the causes of natural death in the United States, heart disease, heart disease, stroke, chronic lower respiratory disease, Alzheimer's, diabetes, infectious diseases, non-infectious diseases, what you'll see here is a very clear pattern. You'll see that the natural cause of death peaks 1 to 3 weeks after the shortest day of the year and is at its nadir 1 to 3 weeks after the longest day of the year. And this is, of course, in the United States, which is in the Northern Hemisphere. It doesn't matter. In fact, if you look at influenza and pneumonia, we are right now in our flu season. And here's the key word. Here's the key that I want to show you. We have a bigger increase in heart disease deaths during the flu season than we do flu deaths during the flu season. Think about that. I mean, this is, if there was ever a study or just a graph that brings this home, when there is an abundance of sunlight, look at the death rates versus when there is a dearth of sunlight. Now, you could say that this has to do with the fact, as many have said, well, maybe this has to do with the fact that at Christmas time and New Year's, that's when we have a lot of parties. You know, in the United States, we have Thanksgiving around this time of year, and people get together as well. That's the reason why the flu is so abundant in the United States. Well, and you can see clearly that when you look at flu deaths per year, and every single year here, it's almost like clockwork. We can predict it very well, exactly when we're going to see the surges of flu and influenza and all sorts of diseases coming to the hospital. Here's the interesting thing, though. Here's Australia. And as far as I'm aware, they also celebrate Christmas and New Year's at exactly the same time of year, except they're lucky enough to not have to deal with any flu issues whatsoever. In fact, they can take time off from the hospital because I'm sure their hospitals are not too busy around Christmas time and New Year's. In fact, their flu seasons are exactly opposite of ours. Again, sort of suggesting that sunlight is the issue. If you're interested, this is Singapore, which is about 80 miles from the equator. There is no pattern. And that's because the sun never really goes that far away from Singapore to actually cause a situation I would propose. But let's check in with Harvard and let's see what they say. So in 2009, they had the H1N1 pandemic across the world. And what was interesting that year is that it came very early in July. And so it decoupled this whole idea of the flu and the cold season being together. And they looked at CDC data and they looked at light differences as well. And what did they find? They looked at this and they correlated and they found, and I quote, this is Zeckhauser from Harvard Kennedy School looking at sunlight and influenza, quote, "We find that sunlight strongly protects against getting influenza." So I do believe that this is showing that the evidence seems to be lining up on the side that sunlight is very beneficial. Now, these types of studies that get published where you look at infrared lights in a Petri dish, relieving toll-like receptor 4 dependent hyperinflammation of the type induced by COVID-19, where clearly when you shine light on a Petri dish, you know, people are looking at this and saying, well, how are we going to get this light into the human body at the level of the mitochondria? That's not the type of questions we need to ask anymore, given Glenn Jeffrey's work showing that this type of light is already penetrating into the body, and I would say all of the mitochondria in the body have a window to this type of light. And so really, when I saw this work, I realized that what we needed at this point was a randomized placebo-controlled trial with the use of sunlight or infrared light in some of these diseases. And this is exactly what we got from Brazil. This was published in 2023, 30 patients admitted to the hospital with COVID-19. Half of them at random received 15 minutes a day of infrared light at 940 nanometers. And plus, both sides got conventional therapy. Actually, the randomization was not completely good in the sense that the intervention group actually had sicker patients. They did this for 7 days, and they measured outputs. And every single one, this is the actual jacket that they use. This is 940 nanometer light in this patient, and they put them on the patients. The only difference was they either switched it on or they left it off. So you could not see it. It's infrared. It was at 2.9 milliwatts per square centimeter, very low energy. Here are the results. Even though the NIR group were sicker, they had better oxygen saturation improvement. All of these, by the way, statistically significant. They had better tidal volumes. They could take a breath in deeper with more force. They could breathe out with more force. Their respiratory rate dropped into the normal range faster. Their heart rates dropped into the normal range faster. The lymphocytes that are tasked for getting rid of the virus not only did not go down by 10 points, as in the control group, but went up by 850 points. But here's the real deal right here. They were discharged almost the full 4 days faster from the hospital, those that got 15 minutes a day of this 940 nanometer. So at that point, I was convinced. I could not see another COVID patient in my clinical practice in the hospital, which is what I do, and not get them out at light. So this is a gentleman that was not too long after that was admitted to the hospital on 4 liters of nasal cannula, kind of this type of oxygen. He quickly escalated to 10 liters of oxygen. By the time he was on 35 liters, 100% high flow, they called me down from the intensive care unit to see about whether or not they needed to intubate this patient or not. I came down, assessed the patient, and said immediately to the charge nurse and to my respiratory therapist, we need to get this guy outside. This is an actual photograph of the little hospital that I work at. This community hospital is one of the hospitals that I work at. This is the patient's daughter. This is our respiratory therapist. This is our charge nurse. And this is our patient sitting in the October sun in Southern California, getting 15 to 30 minutes of light. And we did that on a daily basis for this gentleman. He went from 35 liters, 100% oxygen, almost ready to be intubated, to 5 days later, after we started that full sunlight for 20 to 30 minutes, being discharged home without oxygen. It was the fastest that I had ever seen somebody get that that fast. And again, I'm not bringing this up as evidence that this works. As far as I'm concerned, I've already shown you the evidence that I believe that this works. What I'm trying to show here is the magnitude of change that you can see, I believe, in a patient that fast. So of course, I thought I had come up with something brand new, and of course, there is nothing new under the sun, if you would excuse the expression. Florence Nightingale, probably considered by many the founder of modern nursing, said, of all the remedies I've used or seen in use, I can find but one thing that I can call remedial for the whole disease, and that is a profuse supply of fresh air. Secondly, only to fresh air, however, I should be inclined to rank light in importance for the sick. Direct sunlight, not only daylight, is necessary for a speedy recovery. Another health reformer said, go out into the light and warmth of the glorious sun, you pale and sickly ones, and share with vegetation its life-giving, health-dealing power. This was written back in the 1800s, and it was well known at that time that sunlight had healing properties. As you can see here, this hospital was specifically designed to get patients out into the sun. You can see here, these are girls after surgery that are out getting the sun so they can heal. This is a whole rooftop that's dedicated for heliotherapy. Interesting, when you look into the history of this, there was a doctor by the name of Dr. Rollier and Les in Switzerland who take tuberculosis patients at high altitude where there was less oxygen and more ultraviolet light, which is very beneficial. Interestingly, this is an article I think a lot of you would be interested in reading about how this sort of came to the United States and then back to Europe. John Harvey Kellogg, who was the medical director of, at that time, the largest hospital in the United States at Battle Creek, Michigan, went out to meet Dr. Rollier and looked at his techniques and adapted them for, almost sea level Battle Creek, Michigan, which did not have the same benefits. And interestingly, this rise of heliotherapy in 1893, Kellogg showcases the light bath at the Chicago World's Fair. In the 1900s, the transatlantic diffusion, the German market adopts the Kelloggisch Lichtbad, which is the light bed that he had introduced. And in 1910, Kellogg produces the light therapeutics codifying methods in marketing. And so what you see is this sort of a cycle where Kellogg goes to Europe, sees what they're doing, brings it over, copyrights it, and makes these technologies, and then it gets adapted back in Europe with these light beds. Interestingly, Kellogg never enforced any of his patents. He wanted the world to have the benefit from this, and so it was used and copied multiple times over. You can see here the Battle Creek Sanitarium, the largest hospital in the world. Presidents, again, Amelia Earhart also went here as well. And this is where he introduced a lot of these therapies. You can see there was a full blood lab. This is in the early 1900s. This is even before penicillin was discovered. Oxygen therapy at that time. You can see here that the tenants of the hospital, or the patients in the hospital, were basically stripped down. This is the men and the women were separated. This is the men here, basically down in their underwear, outside getting bright sunlight because they saw the benefit of that. Here's some more heliotherapy here. This is artificial. John Harvey Kellogg's medical career was actually financed by Ellen G. White. She was one of the quotes that I told you about before. She highly believed in some of these effects of sunlight and fresh air. In fact, founded the Loma Linda Sanitarium in 1905, which is actually where my alma mater is. This is Loma Linda University today. So there is something about that in my genetics, if you will, from an academic standpoint. But what's the evidence that we have in terms of hospitals? So I'm listing here paper after paper after paper that has looked at this idea of if we bring light into the hospital, does it change things? And you can see here, paper after paper after. I have 3 pages of this, all of these showing that it reduces length of stay, it improves mortality. So I don't think we need more studies showing that it's beneficial. I think what we need to start to do is to review this literature, and we need to actually get out and start doing it. The most recent one, this was a photobiomodulation therapy, reduced length of stay in the intensive care unit, and improved muscle function. So folks, when people are in the ICU for weeks, you know how it feels when you get out of the hospital bed or your own bed for 2 to 3 days, and you're very discombobulated, you are dizzy, you can't make it down the hall. Imagine being in this type of environment, and these patients often need to go to rehab so they can do their activities of daily living. Well, here's a study design. These are patients in the intensive care unit, 60 ICU patients. They got photobiomodulation daily, 15 minutes. Actually, this is at night, interestingly. And this is a triple blinded sham study where they blinded the patients, the assessors, and the analysts. Again, 30% shorter stay, statistically significant. But when they applied it to their limbs, which is what they did in this case, notice instead of having only 100% improvement in mobility, they had a 255%. Instead of global strength being reduced by 9%, it increased by 12%. Instead of hand grip reducing by 13%, it increased by 34%. So again, this is something that you can do in that setting to improve mobility. Again, our hospital environments, LED lights and windows that block infrared light. So I'm going to sort of wrap up here as we're getting to the end here about a case that was told to me. This mother called me and she told me about her son, and I'm going to share his story for you as sort of a cautionary tale and also an interesting aspect of how much light in the right environment could be of a benefit. Okay, so this is at a tertiary center in Minnesota. I actually reviewed the medical records. This is a 15-year-old Caucasian male and had a diagnosis of a terrible disease called B-cell acute lymphoblastic lymphoma. Started chemotherapy in September 2023, was doing well, and then in May of 2024, stopped chemo due to an illness, was admitted to the hospital, found to have a pneumonia, and a bronchoscopy showed mucor. Now, mucor is a flesh-eating fungus, and it probably happened in him because he was immunocompromised with the chemotherapy. So they started him on the most powerful antifungals known to man, amphotericin B and posaconazole. Later that month, so 24 days into his admission, because he was admitted on June 1st, a bronchoscopy revealed a fungus ball. So what does this mean? This means that the blood is not getting to the infection, and therefore antibiotics that are in the blood are not getting to the infection, so you need to do surgery. So they had a fusion, he had a chest tube. Finally, he was transferred to the adult side of the hospital on the 30th for evaluation to remove his left lung. And on July 1st, a month after arriving in the hospital in that type of an environment where there's LED lights, there is windows, he's getting all of the appropriate therapy. What's happened here is that he is getting worse, and he has surgery. So he comes back, he's missing now his left lung, increase in WBCs, culture sent. He starts to get worse because his LFTs go up. They have to stop posaconazole. They restart it again about 3 days later, and he's now on BiPAP. He's getting worse. His oxygen requirement is going up. His fever is going up. His white blood cell count is going up, and they do a CT scan. And this is a CT scan. I want to sort of show you what this is. There are 3 different cuts through his thorax. This is the upper. This is the middle portion. This is the lower portion, and here you can see on the right side of the screen, which is the left lung, it's completely whited out because this is just fluid. There is no lung there. On the right side, we have white, which means it's infiltrated. It's not doing well. There's infection in the upper portion, in the middle portion, and really the only aspect of his lung that's actually breathing is this one fraction of his right lung that's actually keeping him alive down here. So in the lungs, black is good, white is not good. And so because of this, they have a discussion with the family. They say, look, there's really nothing we can offer. Obviously, we can't take out his remaining lung, and we can't, a bronchoscopy is not really going to do anything. We just need to get rid of this infection. So after a long and hard and arduous talk that the mother relayed to me through tears, as she just recounted it, this patient was made DNR. What does that mean? That means when he codes, when his heart stops, they're not going to do chest compressions. They're going to let him die because there's nothing else to do. Now, he's 15 years old. He's completely awake and alert. He's on a BiPAP machine. He's asking questions. And so they engage childlike services to help communicate this to a completely awake and alert patient, and expressed his desire to go outside. And that's what he did. They said, what do you want to do? He says, I just want to go outside. Now, I want to be clear. They were not sending him outside because he thought he was going to get better. He was not going outside because he thought that would help with his treatment. He was just wanting to go outside. And so that's exactly what they did. He went outside. And so these are actual photographs that the mom sent me of what was involved. And of course, when you're a healthcare provider and you can't do anything else and your patient asks for something, you're going to move heaven and earth to give them their last wish. And so they did. They packed this guy up into a bed, kind of a wheelchair type of thing with a BiPAP machine, all of these drips, all of these things. And you can actually see here, this is actually a picture of him. I got permission from his mom to give you these photographs. He's reading notes here. These are some of his cousins. And he went outside. Let me show you briefly what happened. So he went outside from about 2 to 6 p.m. on the first day. Oh, by the way, the physicians gave him about 2 days to live when he was going to go outside. So he goes outside from 2 to 6 p.m. He has a fever, white count of 27.5, which is very elevated. Normal is like 12 or less. Neutrophils 22.6. Next day, fever's gone. White blood cell count down to 18.0, neutrophils 13.7. By the way, nothing has changed in terms of his treatment. He is using something called a Firefly, which does emit some light, but he had been using that before this point. Next day, Firefly for about 5 minutes, TID, fever's gone, white count down to 7.9, neutrophils 4.8. And then finally on 7:20, the fever's gone. He's feeling better. The BiPAP machine is able to come off. His oxygen is improving. And the doctors are scratching their heads. They have not changed anything. They gave him 2 days to live. And I'm not saying that this is a proof or anything. I'm just showing if this is really what's working, this is at the level that this type of stuff can actually work at. So they brought him inside. They did a CT scan to see what was going on. And the mom told me that when they pulled up the CT scan, there was a gasp in the room. Because what you see here on the left is what he had before he went out into the sun. And after he went out to the sun, this is what they saw on the CT scan. Almost a complete remission of this infection, literally, probably within 2 or 3 days, but they waited 5 days to get the CT scan. This is what he looked like after 5 days. In fact, he got better to the point that he came back to the hospital after he was discharged. This is what a CT scan looked like in October. You can see the lung is hypertrophied like it normally should. This has shriveled up, and this is where he's breathing. This boy is still alive today. I just checked in with his mom about a month ago. He's doing well. He's just had his Make-A-Wish. And he's still battling the lymphoblastic lymphoma. He probably will be battling that for some time, still getting chemotherapy, but this infection's gone. And it kind of reminds me of a quote that Dr. Fosbury has mentioned to me a lot of times, and this sounds like it's incredible, but the quote is this: a lack of natural light in our lives has become the scurvy of the 21st century. And I want you to imagine if we were 300 years ago on a British ship and somebody said, hey, just eat these lemons or limes or drink this lime juice. And you saw just a dramatic improvement in everybody. Like people's gums stopped bleeding, people stopped dying. You would think that it's just impossible, that it's magical. But in fact, if we have created a environment, a perfect storm where we have lack of this infrared light, it does seem like it would be magical, but it's really just science. So I would end this. We need to be intentional about getting outside for 20 to 30 minutes per day. I think because 93% of our lives are spent inside, and because of energy efficiency with LEDs and low E glass, this may be the reason for rising chronic disease. We really need to think about inpatient heliotherapy protocols. We need to think about our lighting environment. We need to have the ability to select it by providers in the hospitals. We need an army of volunteers in the community to take them out. We even vet patients. What will it do to length of stay? What will it do to the cost of healthcare? It could drop it. What about finances, beds? There's a lot of questions here that this could really have a significant impact on. And so maybe the thing that's been missing in our lives has been sitting us in the face for all of this time. Every single day, the answer rises and disappears before us on a daily basis. So I say this: the enemy of longevity is chronic disease. So if you know somebody with chronic disease, or if you have chronic disease, I want you to look chronic disease in its face. And I want you to say, without flinching, let's take this fight outside. And with that, I end. Thank you so much.